What I'd like to do talk about in this webinar is really the use of hypervisors in embedded systems. So hypervisors have been around for many, many years, coming from server technology. But really wanted to break this webinar down into what I call the why, the what, and the how. So certainly why could we use hypervisors and where are they being used, specifically in embedded systems? What are the different types of hypervisors and predominant one we want to use for an embedded system, and how is their hardware support, specifically because ARM, as I said, we're an ARM training center, and how the current ARM technology supports hypervisors. So the first big question is, if you're from a deeply embedded background, typically using microcontrollers, why would hypervisors be of any interest to you? And certainly where we've seen them being used are two major areas. First is where we have existing systems, legacy systems, that are well proven, but we want to bring them into a newer area. And the second is obviously the ongoing and greater demand for security in our connected devices. So if we look at legacy first, so many traditional applications we work with, for example, running on something like an ARM7, fairly old technology now, using a simple operating system. These have not really typically been designed to be brought into the modern world. So obviously IoT is the current drive, Internet of Things. People want to bring cloud connectivity through typically wired or wireless technology. And even the growth of flash-based memory with SD card for local storage as well. And having richer interfaces, so graphical interfaces, and being able to utilize modern libraries. To do that with a traditional application and do all of that porting exercise yourself is a certain major challenge. So one of the first uses we've seen of hypervisors is it offers a capability where you can actually sit a traditional real-time operating system alongside a richer, more general-purpose operating system. And obviously from an embedded environment, Linux is certainly one of the dominant areas there. Very widely used, very widely supported. But obviously I think anybody who comes from what I call a real-time background still would say, even with real-time Linux, we need to be aware of the model there. Where with an RTOS we have a very well-proven tasking-based model. We understand priority-based preemption, for example. So one good use of hypervisors is they bring in this capability where we can have isolation between the RTOS application and our general purpose operating systems. But that allows us to utilize the rich nature of something like Linux. As part of Linux we get all the file systems. Of course, one of the important things from a networking perspective is we get good network support with modern support for things like TLS, transport layer security, or SSL type security that any modern environment would need to do, certainly if they're going anywhere out onto the internet. And of course, with things like Linux, you have a well-defined graphics environment. It's a very nice Qt or Qt environment that is, again, widely used but very, very powerful as a embedded type graphical user interface. So it means that we can leave the major application alone as it was on the RTOS and build the new, richer environment in a controlled, and we have inter-application communication via that side. The other area we've seen is that, of course, modern Cortex-A architecture, where only a few years ago I probably wouldn't have imagined using a multi-core system in typical embedded systems. With the modern power models of these become much more available to us. So the use of where you think of only using a Cortex-M is now Cortex-A is a real option there. And within that, the hypervisor technology also, as part of this translation, allows you to, for example, dedicate a particular core to, for example, the RTOS application. So if we had a 4-core Cortex-A system, then we can be dedicating one of our cores directly to the RTOS, so it's still running in a asymmetric, a single utilization model, and giving us the power performance dedicated to that and controlling the interrupt channels. But then using the power of Linux with its symmetrical multiprocessing, its SMP, to further utilize the other processors, but still give us our power and performance model that we require for a real-time application. Another area we've seen hypervisor technology used and multi-core technology used are things like software-defined radio, where we might have only a few years ago used very large FPGAs or ASICs to do custom logic or custom processing. We're seeing, certainly in the audio and video world, the benefit of using higher power processors, because suddenly we can be using a Cortex-A that maybe is running hundreds and hundreds of megahertz, even up to the gigahertz level, as opposed to our Cortex-M system maybe running at tens of megahertz or even into the low 100 kilohertz, megahertz level, where now we can do a lot more processing in software and leaving really only the front-end areas, possibly still as a custom ASIC, or in the extremes, almost all of the level of processing being done in software. And this opens up a whole host of opportunities in terms of things like upgrades, adding new features to an existing application, and building in a degree of future-proof within the system. The second side of hypervisors, and probably, again, looking ahead for things like Internet of Things, is the potential support of security, or the use of security in these systems. So one major benefit we see with hypervisor technology is that you can get a form of hardware firewall between the real-time critical parts of a system and the general purpose parts of a system. So if you have a system, for example, we've seen it on systems where you have multiple network interfaces, but you can actually create pure hardware separation of these interfaces. This means that, for example, shown in the picture here, that the RTOS can only see one of those PHYs. From an actual application perspective, it is transparent that the hardware is supporting two PHYs and a different I/O model, and vice versa for the general purpose system. Again, it cannot see at the application level, and even at the operating system level, it cannot see that there is actually two interfaces on that. So we can completely create this hardware separation between these. And it also offers part of the security model. One of our big challenges going forward on security is going to be over-the-air upgrades, OTA upgrades. We're now moving into a world where we have to accept that any system that's going to be connected needs to have the provision for upgrades once it's out in the field. And historically, for embedded systems, that has been either something we've not necessarily had to do or had very limited need to do in a controlled environment. And our ultimate goal is where we can actually do this using the utilization of the networking channels to fix bugs, to add new features, and to enhance the application. And the hypervisor technology gives you capabilities to bring up bits of the system at a time, again in a very controlled, very, very isolated manner. And also for many people coming from a high integrity system, for example, where you've worked with real-time operating systems, then there's obviously still a degree of trustworthiness for general purpose operating systems. These large, rich operating systems like Linux and Android are a very broad attack surface. There are, as we know, constant attacks on these, and constant where these have actually been, certain aspects of them do get attacked and do get broken. By using the hardware hypervisor separation, then we're not exposing our real-time part of our application, our real-time control, to that operating system. So if the operating system exploited, if the driver level gets exploited, it still means that our RTOS can be managed, and we can guarantee, for example, utilization of processors at the RTOS level, so we can ensure that even if the general purpose, there's denial of service against the general purpose operating system, that will not affect the performance of the real-time operating system part of our system. So it adds a whole host of capabilities, security capabilities, that is very difficult to build, for example, in a traditional microcontroller type environment. Certainly other areas we've seen it used in, and one certainly interesting area personally for me is the use of agile development techniques for embedded. The challenges of doing agile with embedded and semi-flash-based system is that with hypervisor technology, you have this ability to build isolated builds. So if we have a variant of a code base supporting multiple platforms at the hardware level, then our test platform allows us to spin up particular builds and go use configuration management tools and use our integration tools or Jenkins type tools to actually allow us to load up a clean build and a clean image, so that we can ensure that for that particular test environment it's not being tainted by previous builds or previous tests, without us having to completely restrip the machine back down again. And obviously it gives us a higher throughput in terms of build and test in an agile environment. Other particular areas we've had is As I already mentioned, this going back to the support for over-the-air upgrade is where you may have a legacy system running. You can bring a complete new image in and spin that image up, get that in line with the current image, and ensure that the new image is in sync and utilizing before shutting down the old image. So it has a totally different model from an update perspective. And a slightly unusual one, and certainly one we've been involved in, is the ability to support training, where again, through hypervisor technology, you're offering absolute unique builds. So you're guaranteeing that the training environment is actually an exact replication of the building environment within there. So you're not having to worry. So when you're training on new software, new facilities, you can ensure that the experience that the customer gets as part of that scenario exactly matches what you expect. So hopefully that gives you some ideas of why hypervisor technology, there's a lot more you can do with some of the core areas we're seeing it being used today in embedded systems and that capability. So the next section is, well, what really are they? What are we talking about when we talk about hypervisors? And ultimately, the whole goal is to do with forms of isolation, is looking at isolation and differing degrees of isolation from a build perspective, from an application perspective. So if we look at types of sort of isolation and virtualization that exist today, we can see how hypervisors fit into that particular roadmap associated with it. So the first case is, if you take a modern microprocessor, say Cortex-M processor today, where we're using a real-time operating system, then we do have our first level degree of support, and that's typically through things like a memory protection unit. So certain of the Cortex-M, for example, will support a memory protection unit, and that gives us our first level of isolation. So it means that we can protect certain regions of the memory area, particularly regions of the RAM area. So, for example, when one of our tasks is running, we can ensure that it can't access the other tasks or the main stacks. We can control heap overflow and heap usage. So the MP can be used, but of course we're still dealing with a direct linear model there. We're dealing with a flat address space, we're dealing with a physical address space. And the Cortex-M has a first degree of sort of a privileged level as well. So you have a privileged mode and user mode that you can swap between. So it starts to give us our initial foundation of safety and security at the application level, that we can say, well, if task A is running, then we can ensure that certain faults cannot happen, or if they happen, for example, there's an ill-defined pointer that can be caught through the MPU and an MPU trap into the processor execution model, exception model that we can then deal with in that appropriate way. That's still fairly limited and obviously doesn't deal with many of the other aspects, that the broader degree of security and safety. So the most common one people may be familiar with is our traditional program or process isolation you get in a Linux type system. And you know, this way I have Linux or Mac or OS X or Windows all follow this particular model where we can have multiple programs running. And this utilizes the memory management unit. So at this level, we would expect a memory management unit, so a typical an ARM an A9, ARM11, for example, support the MMU, and that's required by an operating system like Linux to give us this program isolation. And this is done through using a virtual memory model. So the application sees a linear address space, but it thinks that's the physical address space. But the MMU is then doing this translation to the physical addressing. And the benefit of this level of virtualization is that each program, each main, if it, for example, crashes, or it cannot bring down the other program. So it's a first step in terms of giving us a form of isolation. But what we start to get with hypervisors is the next form of isolation. And rather than being just at the application level, so we have to write all applications for Linux or for Android, etc., I'll start with type 2 hypervisors. These are the more common that you may have had some degree of familiarity with. So typically things like VirtualBox or VMware Workstation you may have heard of. And this is where we have the idea of a host and a guest operating system, sometimes referred to as a hosted hypervisor. So we're running a main operating system. So for example, you might be running, for example, I'm running OS X on a Macintosh. But that then allows me to run I use a particular hypervisor called Parallels, and that allows me to run Linux images, so I can run Fedora and Ubuntu images on my Mac, and also I can run a Windows, so I run a Windows 7 image as well. And that gives me degrees of isolation, so I can have pure isolation of the guest OS and guest applications from the host applications, or it gives you the ability to share things between those applications. And that's fairly good, but obviously there's a degree of inefficiency there as we've got host operating system, what it can do. So our real interest is what's called Type 1 hypervisors. And these are the general hypervisors you'll see being used in the embedded system world. And the difference of a Type 1 hypervisor, it doesn't have this host-guest model. We have a hypervisor. Sometimes it may be referred to, and actually is what's referred to as a microkernel. So it is almost a mini OS. You can think of it almost a mini operating system in its own right. And it's sitting between the hardware, and we have pure guest operating systems. And the key difference here is these guest operating systems can be completely independent operating systems. So again, I can be running things like Android and Linux and Windows side by side on my hardware if necessary. And of course, those guest operating systems don't just have to be rich operating systems, they can be real-time operating systems. So it brings in this real power that, in the same way that typically to support this, for example, if you had a PC and you wanted to run Linux and Windows, obviously one way there is you end up having to reboot the machine and you boot into Linux or you boot into Windows. And that's a fairly inconvenient model and obviously not appropriate for any sort of real-time control system. Where this allows us to have the two operating systems running actively at the same time side by side. And the hypervisor has the responsibility of doing that scheduling management between those operating system applications. And the whole number of them out there. Probably the best known one of this hypervisor technology is one based called Zen. Zen is very widely available, supporting on a very wide number of platforms, and has good support for a number of guest operating systems sitting above it. In the security world, in the safety world, there's one called Cell4 that again is a derivative of some earlier ones. Again, these particularly Cell4, it's very particularly specified and targeted at the real-time embedded application. And for anybody involved in avionics systems will be familiar with ARINC 653, and part of it, ARINC 653, is the requirement for this type of application isolation. So you'll find there's a number of commercial hypervisors available, and they will quote ARINC 653 as part of their support. And obviously what we've seen in automotive is the automotive industry adopting a lot of techniques that have been around, for example, in avionics for many, many years. And hypervisor technology is, again, a very good fit within the automotive industry, and again is already being used for isolating things like infotainment systems from other parts of the system, and we get this pure isolation between these. There are a number of commercially available Type 1 hypervisors, again, it's very specifically targeted at the ARM architecture, and of course there are Intel also support there, but ARM is obviously more prevalent in the deeply embedded space. So the three major players, there's a number of other players out there, but Mentor, Green Hills, and Wind River all have their own hypervisor, Type 1 hypervisor technology. And naturally, the benefit of those is they support their own proprietary operating system. So, for example, today, if you're using Nucleus RTOS, then Mentor naturally have the support for that. Green Hills support their Integrity real-time operating system through their Integrity multivisor, and Wind River naturally support the VxWorks RTOS on those. So these have a if you're using these operating systems today, of course, this gives you a very natural and easy transition model into this, this hypervisor model where we can spin up another operating system as an example from that. I say there are many others available to us sitting outside of that. Now, in terms of the different types, the way what hypervisors offer, the other key term you'll hear used when people talk about hypervisors is the concept associated with what's called full virtualization and para-virtualization. And the important difference here is with full virtualization, then a full virtualized hypervisor means you can take a stock operating system. So I could go and get and download a direct version of, for example, Fedora, and utilize it and its device drivers without having to make any modification whatsoever. So I can use it in its purest image associated with that. On the opposite side, paravirtualization, and sorry, the way that the full virtualization works is that the hypervisor then has to have built into it the ability to trap the I/O model specifically. And this, you'll see some of these hypervisors will actually have a direct I/O model supporting them. So they'll trap memory accesses, specifically where we're dealing with the peripheral interfaces, and that do device emulation. And that will allow you to map through from a guest OS to a physical interface. So if you've got networking support, you might have a Wi-Fi support on your target hardware, then you want your guest operating system and guest applications to utilize Wi-Fi as well. But that means that there may be a translation from the device driver for the guest OS to the actual device driver required by the hypervisor to drive the physical hardware. Some are very clever. They can reutilize and repurpose the guest OS if the hypervisor is sharing certain common technology with the guest OS. And obviously this is you see this a lot with Linux-based systems, so that there's a closeness between the driver models. With a paravirtualization, for paravirtualization support, then there is a requirement that there are changes made to the guest OS, especially at the driver level, to create a well-defined API interface, application programming interface, between the guest OS and the hypervisor itself. So there will be specific work done. So you'll find that if you wanted to use a particular hypervisor like Zen, and you wanted to use it in the paravirtualization way, there'll be a particular spin of an operating system specifically for that. So you could go and get, for example, Ubuntu to run on the Zen hypervisor that's paravirtualized. Most modern hypervisors will actually support both full and paravirtualization. So if your operating system isn't supported using paravirtualization, then you'll typically have the case to run it as full virtualization. The reason why I might want to use paravirtualization, there are certain performance gains that can be made through paravirtualization. And also, if you're using an guest operating system that is being ported from a different hardware platform, then this is where paravirtualization can be a benefit the driver. And this is more typically if you want to take an existing operating system, something like FreeRTOS, and you wanted to move that over to a hypervised model, then you will need to do a certain amount of work to do paravirtualization of FreeRTOS to be able to run on a hypervisor technology associated with that. So finally, just to finish off, is explain the hardware support and what's going on at the hardware level. ARM at the Cortex-A level have actually always had a form of a hypervisor, not normally being referred to as hypervisor technology, but they actually have something called Trustzone. So Trustzone is their hardware for support for a trusted, secure environment. And this has been around for many years. It started in the ARM 11s, and certainly has been in the Cortex-A family. And this has the concept of a secure environment and a normal environment with a secure monitor. So this is a form of hypervisor technology and using hardware support for this. So there is a first degree on certain Cortex-A where you do actually have a degree of parallel virtualization using this secure, non-secure mode. So you could, even though you wouldn't necessarily want a secure environment, you could run your real-time operating system in a secure type environment and run Linux, for example, in the normal environment, and that will give you a form of paravirtualization straight away. But in addition to that, the ARM, again, especially on the Cortex-A series at the moment, there is also a separate support for pure Type 1 hypervisor as well. So you can have Trustzone and or hypervisor technology as well. So we could be running hypervisors without the Trustzone. And that has additional support for hypervisor support within the ARM architecture. And this is simply done by adding an extra level of translation. So with normal, like when you're running Linux and you've got the memory management unit, that is normally doing virtual address to physical address translation. And to support hypervisors, what you have is this concept called an intermediate physical address. So you'd have your guest operating system running in the virtual address space, and then the first level of translation tables would be utilized to do the translation from a virtual address to this intermediate physical address. It is then the hypervisor's responsibility to then map this through and has its translation tables, a second level of translation tables, that would do the mapping through to the physical address. Now, there is overheads here, without a doubt. Now, once the system is up and running, those overheads are diminished, but the first setting up, there are a certain amount. So we have to appreciate, in the same way with a standard process model of a translation table, that once we're going from any address space model to another address space model, there is translations. But we're countering that with the fact that we're running on processors with very, very high clock speeds and very, very high performance compared to a typical microcontroller. So again, the use of hypervisors has to be balanced with a particular model. The other hardware support you get, again, to improve performance of the system is the support for the interrupt model. So key to any real-time system will be interrupt support. So the modern, in the ARM system, for example, the generalized interrupt controller, the GIC, has this concept of physical interrupts and virtual interrupts associated with that. And this means that the hypervisor can then generate from a physical interrupt, can generate a virtual interrupt to the guest OS, and then it will manage it through that particular model. And this is how we can do hardware isolation of the actual interrupt model from different guest OSs. So they don't even know they exist. And the hypervisor they can then choose mapping those systems through. And one thing to be aware of is that ARM announced as part of the Cortex R family, and the R has been heavily utilized in the automotive industry, is that on the new V8 R series that there is going to be hypervisor technology support within that. So this will give us safe tasking and give us this isolation model, again, along the lines of the ARINC model. So we can start to have guaranteed hardware separation, but at a real-time area as well. It's worth noting for the ARM V8M that the Trustzone technology utilizing there is not hypervisor technology. It's purely a trap model. So just to finish off, some final notes. First of hypervisor technology, there are naturally going to be performance and scheduling implications of using it. So you have to look at the hypervisor technology, you have to look at the ability to support this thing called process affinity, where we can map RTOSes, for example, onto cores and manage that scheduling, and the guarantee of performance for a particular guest operating system. This is one of the key things in real time, is a good hypervisor say, I can guarantee that this particular guest operating system will not be, the performance of that will not be disproportionately affected by the guest operating system, for example. One of the downsides at the moment is there is no common RTOS model across hypervisors. So this typically means that there will be paravirtualization. And possibly Synthesis RTOS may be a platform here going forward on ARM where we get a better support for hypervisor technology. And the final word of warning with all these things is, of course, the use of hypervisors does we have this concept called hyperjacking, that rather than attacking the operating system, then if we can exploit the hypervisor, then of course we can still own the system. So like any level of support of operating system, there is a security risk. But of course, the hypervisors tend to be much, much smaller, so have a much smaller attack space associated with that. So hopefully that's sort of giving you a very rapid run through of what hypervisor technology that we can do today and where we're going with hypervisor technology. And I certainly see it being a major part of embedded systems and even in the microcontroller world in the next few years. So it's certainly worth being aware of, and if your architecture can support it, then certainly look at utilizing it because it brings security and safety out of the box to existing systems. So there you can see my contact details. Again, feel free to drop me a line if you've got follow-up questions, and Wolfgang said we'll answer any further questions after. And I hope it's been of interest and given you food for thought. Otherwise, thank you very much.